Hello, everyone. My name is Jana Machutová. I work as a software engineer in Gen Digital, and I like to explore topics around concurrency and parallelism. And I like to introduce you one of those topics today. It's about parallel algorithms, which may make your life way easier if you use them correctly. So I hope you will like it. First of all, let's have a look on our beautiful C++ world. And what creatures do we have in there? There are some more or less friendly. We have, for example, templates which may change colors due to our requests. We have an exceptions which may be thrown everywhere. And we have many more worker bees which serve our purposes as we want. But there are some more analogies, and in the real world we have also the deep, unexplored underwater world, which for me represents in C++ that concurrency and parallelism, which is quite hard to get into, and only few people really understand it and can move smoothly. Like you have to be a diver with a license and experience to really not make a mistake there and not get lost. So if you are one of those divers, you can play with the threads. You can see many locked treasures, and you can swim between a lot of barriers. But actually, time to time, we all need to use parallelism. We all want to speed up our code. We want to run faster. And not all of us are experts in this field. So for this purpose, we have a nice tool, nice boat, which will take us over the dangerous seas. And that boat are actually parallel algorithms, which I will talk about today. So what are they, and why are they so great? I will call them standard library next generation, maybe, because actually all the function which you have in a standard library, you can now use in parallel. It's the same, but now you can use them in parallel. You can use them even more. Everything you know from standard library, you can take and parallelize it. It only introduce one extra parameter, which is execution policy, which if I oversimplify it, it just tells, okay, I want to run it sequentially, or I want to run it in parallel. That's all work you have to do to use them, basically. So please don't reinvent a parallel wheel, as well as you don't write your own sort function. Don't write your own parallel sort. It's already there for you to be used. It's well optimized, the implementation is great, it's there for quite a long time, so it's a really way to go. And a really great benefit of it is that you can really easily switch between parallel and sequential solutions, so you don't have to have two different pieces of code. You don't need to have the two different pieces of code, one parallel and one sequential. You have just one function and just change the execution policy. And it's all you need to do. So it's really easy to debug it, really easy to measure it, just switching really fast. So let's jump to the example to see how does it really work. And first I will show you the old way, how we are used to do it. So we have some different species of animals. We have a whole array of them. And each kind of animal can live their life independently on another kind. Fish can swim in the water while the birds are flying. They don't interact at all. So they all can run in their own thread. So what we will do in the old way, we will have a vector of threads. And for each animal, we will just spawn new thread and make them do what they do in their life, like fly high. So how will this look like with parallel algorithms? It will be this easy. There's no threads. You don't need to create threads. You don't need to maintain them lifetime. It's all encapsulated in this. All you need is that array of animals and that one for each cycle. And it should behave almost the same, but what will happen if I have more species, like the life is pretty rich. There are a lot of animal species. There's quite a lot of thread now, right? And I will run out of my resources. It won't work like that. But in parallel algorithms, the big advantage is that there's a hidden threat management underneath. So you don't need to worry about those implementation details. Like those examples, I ran them myself, so it was really split like this. And you see that there are not spawned unnecessary number of threads. It's just distributed reasonable. So you really don't need to have a deep knowledge about what's going underneath to be able to parallelize your computation at that moment. So just to show, this is all you need to do. This the very first parameter is that execution policy. Oh, sorry, the sequential one. If you don't write any policy, it's like if you write this one. If you want to parallelize, you have this one. I will go deeper into the policies. There are more of them, but for now, it's all you need to do to switch from the sequential to parallel execution. So, where can I use it? It's not a new feature, so I believe all of you can use it as it's since C++ 17. There were a few updates in C++ 20, but yeah, from C++ 17 you can use it. There's that clever threat management underneath, so you don't need to care about a lot of things. And what is interesting, there are several new algorithms which are introduced, which haven't been in standard library before. And also some of those algorithms which have been there can't be given that execution policy. They can't run in parallel. Those two groups have something in common, and I will go into that very soon. And what's a pity, it's not available for ranges, so you will see all the examples with the begin and examples. It's not possible to run on ranges. So let's go back to the new and old algorithms, because it sounds confusing. I said like the whole standard library you can use just with the policy, so why there are some which are different, and what's the point? So those are three unlucky algorithms which are not able to run with execution policy. And those are their counterparts. Actually, under the water, there are those which run with parallel with execution policy. It doesn't mean they can't run sequentially. They can run sequentially, even sequentially, even parallel. Just reduce, transform, reduce, inclusive scan, and exclusive scan. But accumulate, inner product, and partial sum can run only sequentially. So I draw an arrow between them, so it means there's some connection. And it's also quite confusing, because if you look up for the documentation for accumulate and then for reduce, you will hardly notice the difference. It seems like it's describing to exactly the same. There's just a small notice which may escape your attention. So I will go through all those pairs so you can see and understand the difference. And if we will cover these few, you will understand it all, because otherwise it's very simple. So let's start with the accumulate versus reduce. We had the animals before, and now we have also a vector of the amount of animals we have. Like there are 68 fishes, there are 15 rabbits, whatever. And I want to know how many animals are there in total. So accumulate seems like a right way to do it. Reduce as well. It seems exactly the same. It gives exactly the same output. But there have to be some trick, right? Because there's also default parameter. Accumulate doesn't necessarily sum up things. You may define whatever operation you want to do on this vector. By default, it's a plus, but you can put there whatever you want. So what if we change it to different one? Let's say we are really optimistic and our animals live happy life. So we expect that next year there will be twice the population of each of them. And we want to know how many of them will be there next year. So our function will change. That function, default, takes two parameters. It's two items next to each other. It's for the very beginning, there's you notice the 0, there's the initial value. So the 0 is the first, 68 is the second, and you do that operation over them. So I want to multiply 68 twice and go through that. So at the end, I will get the correct number. But there I have a different output for both of them, which is a bit unfortunate. Like, it seems like it means that the parallel version is faster but not correct. Don't know if we are happy about it. But we can have a look why is that, and to understand it, I will walk through what's going on. Like, the sequential version is quite straightforward. Like, you get the initial value, get 2 times the first item, and sum it up together. I think this doesn't need much of comment because it's really what you imagine under the accumulate in this way, and you have the correct answer. But what happens when you reduce it in parallel? If you want to do something in parallel, first thing you do, you split your data into small chunks. So I split it once, split it twice, and now I have pairs, and I can do one operation on all the pairs at once. Yeah, meaning parallel. So I will do that simple operation. Now I have reduced the data set, do it again, and that's and then there I have the answer which is wrong. And why it is wrong? I put it down the line what actually I was computing, and then it's not the same what the sequential version do. The trick is that the operation I define is non-associative. And when you split the data, you no longer keep the chronological order. You mess them up, so if it's not associative, it can't work. So basically, the accumulate work for all the functions, but the reduce work only for the functions which are associative. Otherwise, you break everything down. So that's the reason why there still stay accumulate, because you still may need it. You still may need some associative operation, but you can do it only sequentially. And then there's a reduce. Every time you can use a reduce, every time you do associative operation, you reduce. You can do it even sequentially, it's okay. And keep accumulate only for those special cases. So, how can we fix that? Can we fix that? Fortunately, there's also a version of reduce, which is transform reduce, which takes 2 operations. First, it transfers all the elements, and then reduce them. So I will first multiply every item in the counts, and then sum it up. So the plus, the reduce operation, the important one, is associative now, and it will be just okay. So it's possible to fix like this, not always. This was a very simple example, but it's demonstrate what's wrong in there. So if we will fix it here, it will look just like this, and we have a correct answer. We just pushed the multiplication at the very beginning, and then all the parallelization works just fine. So the second pair is inner product versus transform reduce. So with the inner products, we have the counts of the animals, and they have some weight, like from the small plankton till the big whale, probably. And we want to know what is the whole mass floating in the sea. So we want to multiply 1 times 68, 2 times 15, and sum it all up. We can do the both way, inner product and transform reduce. And now you can see it's a different flavor of transform reduce, which accept 2 vectors actually, not just one. But yeah, you can expect that this will work fine. Probably you already know what will be wrong, what can go wrong. There are also those parameters, one from transform, one from reduce. And they have to stay associative. But I can break it a different way. I will make more realistic weights there. Actually, I was looking for the smallest one and the biggest one. Smallest one was some small plankton, which they were possible to weight, and the biggest one should be big whale. the between doesn't make sense too much. But those values can break my computation too. It's not the same. But I still have multiply and plus. Does someone know what's wrong in there and why it's different? Sorry? Oh, yeah, it's floating point arithmetic is not associative at all. So it's the same problem, but it's good to mention this one because when you are doing floating point arithmetics and you will put it into that parallel version, you may get different result, but it's not really like it's wrong result. It's yeah. It's good to know that it may happen to you. What was my fix in this version was just putting it into double and the bigger precision to make it work. But otherwise, yeah, just be aware that floating point arithmetic is not associative, which give you different results, and it may really confuse you. Like, what am I going wrong? You are not doing wrong anything. So the last couple, it's not really couple because partial sum has two counterparts. More closer is inclusive scan, but there's also exclusive scan. And to not get lost into that, I will first illustrate what partial sum is all about. It's basically accumulate, which gives you a whole vector of results. So you count together the previous result with the actual item, like in the accumulate, but you give back a whole vector. Inclusive scan is basically doing the same, while exclusive scan, you say the exclusive, it doesn't count the current item. So the exclusive scan has the initial value, which is returned for the first item, and on the second item is included the second one. So I think the illustration, it's illustrated like hopefully well, and so we don't get lost in that. So let's have some example about this one too. So we want to know how many food will be there. As we know that our animals are sorted from the smallest one to the biggest one, so we can say that the animal which has can eat itself and everything which is smaller. It will hardly, like small fish will hardly chase for sharks, but shark can hunt for all the smaller fishes. And yeah, so it seems like a good example for partial sum, maybe. Also with the growth factor, it will destroy it all. You already know it, right? There will be non-associative operation. So what am I doing? I'm going through all the weight which is available to eat, and I'm giving back how many food is for given species available. To do inclusive scan, it's exactly the same. And will be the output same? Well, it won't because of that associative operation. But even though you already know what's the wrong, I would like to guide you through inclusive scan workflow. It's really nice to see how it's possible to parallelize some computation. It's naive way a little bit. It's possible to do it better, but it's nice to illustrate how it can be computed. And I will show it on without that growth factor, so you can see correct results, how it really fits together, how it really works. So we have this array of weights. I will put indices there. It will really help us to find out the magic. And the first one, yeah, it's the same. You don't sum it up with anything else. The second one, you can't, in parallel computation, you can depend on the result of the current step. So we get so I don't get the 68 from the result, but for the source. And I will go with all the way. I will sum just always the neighborhood, the previous one and current one, which is definitely not the result we want to do. But we get some interesting intermediate result because those two are already correct, right? So we just can copy them. And what are we missing on number 42? There's item 1 and item 2. So we are missing just the 0, right? We will put this there. The other one is 2 and 3. We are missing 0 and 1. You can see the pattern in the arrows. It's probably will be working on others too. So now we have 4 items which are correct. And probably with the larger distance, we will get to the final results. First 4 are okay, and just put them together with the last. And you can see the values are correct and the indices fits. Everything has 0 till its number, and it's all. So this is the way how you can parallelize this computation. Of course, you have to keep associative function inside. So can we fix also by some transform our example? We can try it and do transform inclusive scan. It's there available too. We will again transform it by that growth factor. Every single item in mass we will multiply by 2, and they will sum it up. So will it be the same? It's not the same. And actually, I think this transform inclusive scan is better because it actually multiplied even the first item. The previous, the partial sum, just take the first and multiply the second. So it was actually wrong. But it's not the same result, so maybe it's not what you wanted. So maybe we can try it exclusive scan. Maybe we can get better results. So let's try to switch it from exclusive scan. And exclusive scan has an initial value. So we want that first item to be initial value if we want the same result. And just put the rest of the vector, like the input vector. So we will get correct values, but not all of them because we have shorter vectors. So yeah, it's up to you how to solve this. I think the transform inclusive scan is actually, in this case, the correct solution, but it's just good to know what are your options in here. So having that, those are algorithms which are exceptions when switching to parallel algorithms from standard library. And if you know those and those, you are okay to go. You can just use the execution policy and you can use it. Just be aware of those, and all of them have the same trap, so it's not that hard. Always prefer those underwater. They are just, if you have associative operation, always do the underwater. Keep those old one just for the special situation, and you will be just fine. So, yeah, as I said, all others than I've just presented can run in parallel without no problem. But of course, some different algorithms are possible to parallelize with different efficiencies. Something is easy to parallelize, something is pretty hard. So some of them may require additional allocation inside. You don't have to do anything, but don't be surprised, it may do some additional allocation. Maybe in your implementation, some are not implemented so far, but the worst you can get is the sequential performance, so don't worry about using that. Different algorithms are performed different. Sometimes you gain a really good speed up, sometimes it's worse, but yeah, it's all you need to do is add an execution policy and measure it all, find out if you really gain something, but the use is really easy. So just show you that it's not about for each only. There are more algorithms in the StarNet library, so we can, for example, find shark or sort our schools, do whatever standard algorithms you can think of, and try to use them all. Not stick to the for each, like each of us often do. And this is all you need to do. But sometimes you find out that it didn't speed up your code. Well, as I show you the examples, they won't speed up at all. There were 8 items. well, it's not worth to launching a new thread, right? So small data won't benefit from parallelism. And but the implementation beneath are smart, and you don't get worse performance than you have in sequential, because, yeah. As I said, the efficiency is different, and what can become a bottleneck is synchronization. So always measure your code, find out if you really gain something, because it's not like for sure. And I will go and show you the synchronization, which may become that bottleneck. I want to put all those weights and foods and counts together into one small example, where we have some amount of animals which are there around in the year 2025. Then we use transfer to find out what amount will be next year. We will run it nicely in parallel. Then we know what there will be amount. We want to know what will be the total mass of the food in the tier. And at the end, we will find the food for each species, just as we saw it before. But the problem is that we run each of it, we run in parallel. I don't know why I run exclusive scan in unsequence, but why not? But what's the problem are those points where you have to wait until everything runs, until everything finishes, and then launch another parallel workload. But you don't want to look at it like this. You would like to see this one instead. It will be much faster, right? You don't need to wait anywhere. There is one trick which can be used time to time, and it's to use a view to actually, if you put your view to transform exclusive scan, it will go just like this. You will create a view which is evaluated inside that, so you don't get to that synchronization points. That's just a small trick, like think about passing a view inside instead of synchronize that. So, what I haven't mentioned so far, I mentioned multiple time execution policy. I said there are more of them than sequential and parallel, but it's good to know how they really work. So there's all list of all execution policies available so far. So we can find a shark in a sea in sequential, parallel, unsequential, or parallel unsequential. I will go through each of it to show you the difference and different approach and what you have to take care of when you are using it. So sequential, the simplest one. Your code is executed sequentially. All the computations are executed on single thread, one by one. No parallelization at all. And if you don't define any policy, if you use standard library functions, it's the same like if you write execution sequence sec. It will look like this, no surprise. And I will build up an example. I will modify through other execution policies. So we have a fish school and the indicator if there's some shark nearby. And we go through all the fish. And if I'm not a shark and I see shark, I will run away. Otherwise, I will just float. And at the end, I will update the shark nearby. If I'm shark, I will indicate that there's shark nearby. I hope it makes some sense. In sequential, there's no big deal. You can do whatever you want. It works just fine. We will see how it will work in other policies. So, parallel. Code is executed on multiple threads. You can predict the order in which elements are processed, and you need to protect your shared data. I said it's easy to use parallel algorithms, but you still need to care about it. It's not given to you like, oh, I have shared memory, it will deal with it somehow. No, you have to deal with it. You have to protect your shared data, access to that. And by using that policy, you give a promise that you took care of the shared data, and that it's possible to parallelize it. It's your responsibility. So good to notice is that when you need a blocking protection, you probably won't perform that well. It makes sense, but so you have, for example, 2 threads, and 2 attempts at once wants to change the counter. If they won't protect it, it's a data race like everywhere else, so you need to lock it or make it atomic or whatever before putting the execution parallel there. You have to take care of it. So what about our example? We want to put it into parallel execution policy. So what can we do with that? We have that shark which we modify inside for each, which is not possible like that because it's a shared. So we can do it atomic, and for this policy, it's absolutely okay. You can put the locking, atomic, whatever you know, and you are okay. Everything will run just fine. So I have atomic boolean, and I'm atomically updating it if I'm shark. So it seems, but what are the other execution policy? Like we have sequential and parallel, and it seems like we covered all, right? But then there's also unsequential. It's executed on a single thread, but the whole data, whole vector of data is executed together. Like it's parallelization on one thread. It's so the instructions are in unpredictable order, and there's absolutely no synchronization allowed. You can't use atomic, you can't use locks, nothing. You simply can't access the shared memory at all. So how does it look like? You have a bunch of items executed in once, and then another. So what you want to do is locking counter when you're accessing it, and then increase it. But you are doing for 4 items at once. What may go wrong? The operations are mixed, and now you are locking the counter, and locking again, and locking again. And I think you can't lock multiple times, right? One lock. So it's not possible. It won't work. You can't do any synchronization out of it. It works just from data which doesn't use any shared data. So how can we proceed with such an example where we obviously have a shared indicator of shark? Well, we can do that much about it, but we can split it and compute it ahead. And we can still do it in parallel. We can find if there's some shark before we used it. And it's absolutely okay because it's not changing then. And then there's the last but not least, there's par-unsec. Let's combine all of it together. It's on multiple threads and it's vectorized. So it's strongest possible version of parallelization. And it has actually the same limitation in unsec. You can hardly think of any more strict. You can't use any shared data. No synchronization is allowed. And this is the one you should target if you try to parallelize, because if you can't use any synchronization and you are able to do so, it means that it will perform well, right? Because what limits the performance is the synchronization, which is there when you are sharing data. You need some synchronization. So if you are able to target this one, you will gain the most performance. Just to show how does it look. Another counter, 2 threads with vectors is the same like before, so don't even think about that counter. You can't. And yeah, for that one, I have different examples. So you are swimming in the sea, and you want to take a picture of the fishes which which you like. So in sequential, you will just go through the fishes, and if the fish is nice, you will just take a picture of it, right? And push it to your SD card, which will be tricky, but in parallel it's possible because you can lock the access to your SD card. So you can run it in parallel, but could you do something like that in parallel unsec or unsec? Do you have any idea how to do such a thing? No. Well, the key to this is not use for each for everything. There's so many algorithms. There are some which may fit your need, and you don't use for each for everything. That's the solution for a lot of problems. So I hope there's a clear difference between these policies, and it's all nice, but there are some downsides of parallel algorithms. You see that everything is a black box. You don't know what's going on under the cover. You just believe that it will be parallelized well, and it will be. It's written really well usually, but you have no control about the threads. For example, you can say, oh, I want to run it on those threads and those many threads. You can't bind them. You can bind it to specific core, and all tasks run in the same system priority. You can't do anything about it because you just believe the system underneath. And it may become a problem sometimes, but yeah, that's the downside, which is good to know about. And another one is that there are the hidden thread pools, which are great, they're useful, but you don't want to mix them with your own parallel runtime because you can run into oversubscriptions. So pick only one parallel model, like you have OpenMP. Never nest them, because I will show if you will do something like this, that OpenMP will split your tasks into different threads, and for each parallel will do the same, and they will clash over. So never mix them up. Always think of it that there's already system hidden underneath, and you don't want to mix them. It may make a huge mess. So it's quite powerful tool, but it has its limitations. So it's that small boat which helps you but doesn't solve all your problems. If you have problems with those things I just mentioned, you need more powerful tools. Either you write it by yourself, everything, or there are huge, powerful tools to come. And no, I won't talk about it. It's huge things which is to come in C++26, but it's much larger than parallel algorithms are. But it allows in the future just a sneak peek what may come, not even in 26, but later on, based on the TD execution, that you can address these problems. But it's just an initial paper. It's not done. But you can use scheduler from std execution, and there you can specify where and when you want to run your job, and then you say that you want to run it parallel. But it's just very beginning of the work like this. So you can see in the bright future that even the problems I mentioned might be solved, but it's not there yet. Okay, so what we learned so far. Use standard library algorithms. Your life will be easier. And use the parallel version of it. Your life will be easier and faster. It's really good to use them. Use always the strongest possible policy. When there's need for synchronization, you probably won't get that well performance. And try to avoid data dependency. the synchronization is really what destroys your performance in parallelization. It basically destroys the parallelization. And always measure your performance before and after, which is really easy with parallel algorithms. And yeah, beware of non-associative operations. Thank you. So, do you have any questions?
When you show the example with the view, is that well defined? Because I know that some views can actually cache some stuff inside. So is it actually, always safe to with every implementation of the standard? Because I care about the synchronization aspect, and it's a nice trick. I'm just worried that it might happen to work.
I believe it is, but I've tried it, but just that simple example. I think I'm trying to find it, sir. This one.
Yeah, my concern is that the standard probably doesn't give you guarantees regarding the threat safety of the view itself, but that's the concern. I don't know if you know that there is a guarantee that it will work with anybody.
I'm not really sure, but I'm sorry. I can find out later on. Okay. Something else?
Have you seen any benchmarks comparing the standard parallel algorithms to something like OpenMP or OpenACC?
I haven't done any benchmark, sorry.
Because it sounds like OpenMP would be kind of useless if this, really grows into what
I haven't done any benchmarks, sorry. Well, it's supposed to help you to do things simply, to not care about what's underneath. So, yeah, it's there to serve you, actually. So there has to be some system underneath. So that's the reason, basically. It's the simplification. So, if it's everything, thank you very much.